I'm David Schleef. I'm a Gstreamer developer, which is how the talk got labeled Gstreamer on the little form on the website. But I'm actually going to be talking about Dirac. And Dirac is a video codec video codec format, video compression format that was developed by the BBC over the last 5 years or so to be competitive, to be a modern, state-of-the-art video encoder. And they've done a pretty good job. And a couple of years ago, they hired me as a contractor to write some code for them. And that's what I've been doing for the last couple of years instead of working on Gstreamer. So this is sort of my first talk after everything's been sort of completed and squared away and sort of ready to talk to people about it. So this is actually my first Dirac talk, so see where it goes. We have a website that, interestingly, based on the last talk, I've just decided to move from Drupal to WordPress. I set it up using Drupal, and my experience is that I just don't have the time to learn everything about it. It looks great, it does what it needs to do, but I just I want a website. I don't want to deal with it. Anyway, so this is going to be a short talk, and then we're going to watch some video. I'm going to talk a little bit about video compression in general. I'm assuming that the group here is not all video compression experts, so we're going to talk about a bit about how it works. And then I'm going to talk about where Dirac is today and where we're going in the near future. And there'll be kitties at the end. All right. So this is the next couple of slides are going to be just general about any video compression system, and I hope what I show here is sort of intuitive and sort of gets you an idea of how video compression works. It's not really. You're not going to be able to go out and write, video compression software after this, but it's nice to know how stuff works. So the first couple slides are going to be just about image compression, and this works for like JPEG image compression as well. What we do is we take an image like this, which is relatively complex, and we transform it into different frequency components. And this is just a real basic system right here, where you're transforming it into one low frequency component and one high frequency component. But say like Dirac transforms it into 13, or like MPEG transforms it into 64 in the typical case, or Theora transforms it into 64. So there's lots of variation in how this works, but in general, we're low-pass filtering the image so that we get something that's simpler, and then we subtract the two, and we get something that's mostly zeros, because most parts of images are kind of simple, and then you can see here that mostly what you have are edges and details and so on. So, and the reason we do this, and I hope this comes out right, and I walk back and see. No, it doesn't come out right at all. I have to go to the website. I'll put this up on the website here. This is called the Campbell-Robson chart, and it's developed in the 60s to kind of figure out how the human visual system works. And what we have here, we're on the bottom of the chart. It's varying from black to white, completely from black to white, and the frequency, the spacing of the grading increases as you get to the edge there. And then as you go from the bottom of the chart to the top of the chart, it just fades evenly to gray. And what you're supposed to see, and like I can see this on my monitor right here. You might be able to actually, you might be able to see it on my monitor, sort of. What you're supposed to see is that the parts of the grading that you can see are mostly down in this area. and it sort of cuts off right in here, and then I drew a line here. So like generally, when I look at my monitor at a typical distance, I can see only stuff below this red line. And then the stuff above the red line, you really can't see. And it doesn't really work, does it? It depends a lot on how you're viewing it and how far away from the screen you are. And for the most part, correspondingly, you're all fairly close to this screen in terms of how we think about it in video compression. But anyway, where I was going with this, if you'll humor me, that this actually makes sense. Since we just transformed the picture into some sort of frequency domain, to like here, here we have the low frequency stuff, over there we have the high frequency stuff. If we can figure out how to get rid of all the stuff above there, then we can just throw it away because you can't see it. Unless you get closer to the monitor, then you can see it. So that's what we're doing. That's the second part of what we do. And the way we do that is we quantize we quantize each of the components that we get out after this after the filtering, and that works quite well. And then after that, we take all those quantized values and use standard data compression techniques, arithmetic encoding, entropy encoding. Sorry, I'll just wait for everyone to come in here. We had sort of a lull right around noon, so I just almost. These are 3 frames in sequence, 1, 2, 3. And say we've already decoded these 2 frames. If we want to predict the one in the middle, we can copy just about the entire frame. And it's only going to be a couple places there in the corner where the image changes a little bit. And what we do is we divide the image up into typically about 5,000 blocks. And then for each block, we'll say where to copy it from, which image, or where in the image, and so on. Or if we just want to encode it, not predict it from anywhere, but just encode a separate block, you can do that too. And all of this stuff is very, very common. MPEG does it. Just about every video codec does things in the same way. So of the few tools that I described right here, this is how well each tool helps us. And so standard definition video, essentially what you see in a DVD, uncompressed, is about 167 megabits per second, which is a huge amount. And I don't even think you can, you can't even pull that off a hard drive. There's so much that's faster than hard drives can push off that information. So even doing standard definition video uncompressed, you'd need a RAID system or multiple hard drives or just very fast hard drives. So instead of doing that, we go through the frequency transforms and the quantization, and immediately we can get it down to about 25 megabits. And this is standard video camera digital video, DV. And I think if these aren't high definition cameras, they're almost certainly doing DV at 25 megabits right here. And so the other tools help us out a little bit. The entropy encoding helps. I actually kind of fudge these numbers a bit because DV is actually doing a little bit of entropy encoding. It's just not very good. And then motion compensation gets us another factor of 5 maybe. And then there are a few other tools which get you a little bit better. But I'm not going to go into those. So that's sort of in general how video codecs work, how they do their thing. And then this is my my little hand-drawn chart. I do hand-drawn charts when I'm completely making stuff up. So this is where I'm completely making stuff up. This is sort of my view of the industry and how this stuff works. And so over time here, Moore's law, CPU speeds get much faster. Back in the 90s, about all a computer could handle is MPEG-2. It's just sort of old. You go back even further, it couldn't even handle that. And as computers get faster, the video codecs take up the same amount of CPU. So it's kind of like video codecs just take up as much CPU as they can, and get complex enough that they require that amount of CPU. And because of that, the bit rate over time decreases a little bit. The problem is that we're sort of asymptotically reaching a limit here where you just can't go lower. So I'm going to say, based on my experience, Dirac is it's a little bit better than MPEG-4, but it also takes up more CPU. So I'd like to think that that's the future. And there's a number of reasons why that doesn't matter. Like the amount of CPU power that it takes up doesn't really matter much anymore. I mean, basically the same idea as Moore's law. It's like we have so much CPU power, and on GPUs we have even more GPU power that can do all of this stuff for us. So does it really matter if it takes up a lot of CPU? Not really. So I talked a little bit how video works. And this is a slide or two about how people use video compression. And a lot of people really have experience with like DVD quality stuff, which we call visually lossless. It's basically we decrease the bit rate until you can just barely see any degradation is the word we use. Degradation meaning you can tell the difference between that and the completely uncompressed stream. So visually lossless means you can't really see any difference. And this is sort of the place where everyone wants to be. Just right above that visually lossless bit rate. And that's the thing on the previous slide where I was graphing that. It's going down slowly over time as we increase CPU usage and so on. And then down here, everyone knows about YouTube. And I consider this degraded video. And degraded video meaning you can definitely see that there's problems with it. It looks ugly. You can see blockiness. You can see compression artifacts, all that sort of stuff. And it's good because it's cheap, because you can actually fit it into the channel, into the network link that you're trying to push it through. But it's kind of gross. I mean, everyone would choose visually lossless over degraded if they had a choice, but sometimes you don't, because you don't have that. You don't have the liberty of having a couple megabits. And then the other two here, these are, like I mentioned about the video cameras, these store things on a tape at 25 megabits per second. That's pretty common. And then up at the studio end, they have so much bandwidth, it's almost impossible to believe that they need compression. But as things move from standard definition, which is like a DVD, up to high definition, which is up to 4 or 5 times as big as a DVD, or the screen resolution, it tends to you have to have stacks of hard drives to push all the data around, and it gets very complicated to push that much data around. So even in the studio area, they're starting to use compression just because they have to. It's like they finally gave up and said, okay, we'll accept compression just because we can't do it without. And this is very true about digital intermediate. Digital intermediate is a term for used in movie productions for filming on 35 millimeter film and then scanning it with high resolution scanners. And this ends up being like 10 gigabits per second or even more than that. And then they edit this and then compress it down to a visually lossless, which is actually a lot more than this. And then they ship it out to like the movie theaters downstairs. So this is all being done in the digital domain, and it uses several different types of compression. So, I did this backwards. So I'm going to say, this is me making stuff up, drawing my own charts again, that this degraded type of video is going to go away. Back in mid-90s or whatever, when we all were on dial-up modems and we listened to internet radio and stuff like that, is really bad quality. Nobody ever does that anymore because everyone has enough bits to that they don't, like, nobody will ever, you won't stand for that anymore. So I'm going to say that in the next couple of years, that's going to go away. That everything is going to be visually lossless or very close to visually lossless, and it's only going to be in very few niche environments where you're going to see degraded video. So the compression formats out there right now, these are sort of the five that are competing for most of the designs out there. And then we're going to add Dirac here fairly soon. Of course, the two MPEG-4 standards. The second one, ABC, is starting to become more. I mean, this is probably the best one right here. And then there's a couple more. AVS is actually a standard that's developed in China and being pushed a lot by the Chinese government, which I think is really cool. A lot of other people, like the American government, thinks it's really bad, but whatever. But these three were pretty much developed because they didn't like MPEG. So they were like, Microsoft was spending so much money on MPEG licenses and got so annoyed with the process with standardizing MPEG 4 Part 2 that they decided to write their own codec. Well, they already had their own codec, but they decided to push it a lot more, which became Windows Media Video 9. And the same thing with the Chinese government, and then also Real did the same thing, where the previous version of their codec was actually based on MPEG H.263. So, okay. So now we're getting into the Dirac part. It's like, what is different about Dirac that makes it better? One thing that I think makes it better is because it uses more CPU power, so you get lower bit rate. But that's not completely true, because you can also take all of these codecs and tune them down so that they act a lot like some of the older codecs. So they'll take less CPU power and a little bit more bit rate for the same quality of video, and that's good. And Dirac can do that as well. The things I like about Dirac is that the tools, like the tools I described in the beginning of the talk, are very simple, but they're all very configurable. And this is not the case with like MPEG. Like MPEG MPEG mostly everything is very rigidly defined, and that has a lot to do with it being designed by committee, and like a lot of things aren't really quite done right because it seems like there's too much of an argument while they're standardizing it and stuff like that, and it kind of shows in the design. But yeah, so of course the important part for most of you in this room is that Dirac is completely free. The BBC owns a number of patents, but on the ideas, but has stated that they are letting these be available to anybody for no royalty. And then Dirac is also under the MIT and also for a bunch of other licenses for reasons I don't remember. Anyway, sorry.
Have there been like patent searches to make sure there aren't other patents that are being infringed by?
Yes, the BBC has spent a lot of time. The BBC lawyers have spent a lot of time researching patents and so on, exactly for this reason, because they don't want to spend 5 years developing this, and then find out that their great royalty, or the patent-free codec actually has patents. But the thing that helps it is that these simple tools, these simple compression tools, they're all invented in like the 60s and 70s, and some of them in the 80s. Like, they've been around for 30 or 40 years. So the reason that they were never used is because they take a huge amount of CPU power, and like in the 60s certainly, it would have taken 10 days to compress one image. So but now, like, you can do it in 100th of a second on your computer.
While you're talking about differences, can you mention how compared to Oxford's Theora?
Oh, Theora? Yeah, sorry, I didn't. Actually, there are some Theora developers in the room. Yeah, I didn't. Theora is very similar to H.263 in terms of complexity and so on. Would you agree? Okay. So actually, anything that I would say about H.263 is pretty much true about Theora as well.
I'm not familiar with different implementation. I'm not a developer.
Okay.
More in terms of the goals that you're trying to achieve. Is it pretty similar?
Well, in terms of creating an open source codec, yeah. But I'm not sure. I'm not actually very familiar with where the Theora project is going right now, so I can't really comment on that. So, yeah. And then the other thing about Dirac is that it's designed for now, whereas that's one of the differences. I think Theora, since it was designed several years ago, it's a little bit dated. Sort of like H.263. So, like, these things, you have more CPU power, so we can sort of move on and use new tools. So here's my sales pitch. If any of you are trying to decide between H.264 and Dirac, they're very similar quality, much lower licensing costs, and in my opinion, there's much greater design flexibility with Dirac. Just because the tools are so configurable, if you want to take Dirac and pigeonhole it into whatever crazy application you want, there's chances are you can just twiddle some things on the encoder and it'll work. It'll do what you want it to do. Of course, it probably won't do it well because we haven't really optimized it for the encoders for everything yet. So. This is where the Dirac project is today. As I mentioned, it's developed by the BBC. We have a small team, mostly at the BBC, myself and a couple other people that are working on it pretty much full time. The bit stream, these are the bit streams right here. There's the studio codec, and then also the normal H.264 equivalent codec. These are both frozen now, so the bit streams won't change. And then Schrödinger 1.0, which is the project that I've been working on, is the actual codec, the code that does the Dirac encoding and decoding. And that's been released, and it works quite well. It's a solid encoder. Actually, yes. I guess I've been just saying that. So this is part of the industry support. There's actually a product out on the market. You can buy it. It compresses uncompressed high definition video, 1080p, down into a stream that can be sent over what an SDI. I didn't explain what SDI was. SDI is a serial interface used for uncompressed standard definition video. It's a 270 megabits. And this compresses the high definition video onto that pipe, which the BBC has hundreds of thousands of miles of SDI cable running around all their studios and around all of England. So they're very interested in doing this sort of thing, to compress down to their existing infrastructure. So And I'm actually not involved with that at all. So Schrodinger is our project to develop a fast encoder and decoder and make it a solid open source project and then get it integrated with everything. So, okay, so the current project that I'm working on is to integrate Schrodinger and with everything out there. Gstreamer, if you happen to be a Gstreamer fan and user, then since I'm a Gstreamer developer, that's the only reason why it was so integrated well. It pretty much just works. And the next version of Ubuntu, which I also use, the one that's coming out in a couple of weeks, you put the live CD in, and you click on a Dirac file, and it says, would you like to install the Dirac codec? And you say yes, and 5 seconds later, it'll be playing Dirac video. So that's awesome. I'm really thankful to everyone that helped out in this area. So the only problem is we're a little bit slow on container formats right now. You can play raw Dirac video, but you can't play it with sound. I mean, you can, except I mean, I usually use OGG, but we haven't really specified it very well. And even though Gstreamer works with it right now, we might have to break that because I did it wrong. But anyway. So that's why you haven't really seen any Dirac videos out there. But in the next month or so, I want to get like Big Buck Bunny and Elephant's Dream and all of this open stuff up onto a BitTorrent so that you can download it and say, hey, look, I'm actually seeing Dirac video playing back on my computer with sound. So in other container formats, we're a little.
Just get all those out of copyright silent films.
That's true. That's true. So we have Google Summer of Code projects. Actually, there are a couple more ideas that we're looking in that we have applications for as well. But these are the ones that we've gotten several applications for these two, and these are the ones that we like. One is extension to Cortado. Wim here wrote Cortado. It's an implementation of Theora and a lot of media playback, open source media playback in Java, so that you can pop it up in any in the theoretical Suns, run everywhere, which actually isn't true. But so also as part of this offloading to GPUs, so that we can use all the CPU power that's on the video cards. One person has written a CUDA backend for NVIDIA cards, and then we're trying to get a Summer of Code student for that. Oh yeah, so that's the NVIDIA rendering backend. That increases decoding speed by about a factor of 5, because GPUs are so fast for this sort of operation. And then this is the project that I have failed to release in the last week because I've been working on this presentation. I added a 10-line patch that increased encoding speed by a factor of 3. Yeah. So where we're going, we're always adding encoder improvements. There's a little bit of specification work to do yet, not in terms of bit streams. The bit stream's frozen, but there's still a little bit of decisions on profiles and levels. And my project is integration into everything out there, so that you don't have to ask me, well, what application do I have to use to get Dirac? It's like, well, that's if you have to ask that, we failed. Like, you should be able to use any application. So this is our future projects, which is sort of the limitations of Dirac. They're not very good for that, those back that slide a long time ago. For degraded video, we're pretty much looking only at visually lossless, and we're not very good about that. I want to follow up on that but I don't want to work on that too much because I think it's going to go away in a couple of years. So, and then we're trying to get people involved, and then I'm contracting with several companies for putting Dirac into their applications, and that requires a little bit of tuning. And there's a kitty.